Into chapter 3, and what we're gonna learn in this chapter is radiation, light, and then how the ozone layer protects us from the sun's UV radiation. So we're gonna go through a number of chemistry ideas here that are related to light and molecular structure, and then afterwards we'll get into that ozone layer discussion. But before we can do that, we need to start with discussing the math skill that you're going to need to know in this chapter, and that is to use your calculator to do these type of calculations with scientific notation. So we learned about scientific notation a while ago. So I'm going to move the view here to this calculator simulator, and hopefully you can see it fairly well. What we're going to try to do is calculate those two numbers there that I was showing. So the first one is just 7.50 times 10 to the 14 with 6.22 times 10 to the 8. So multiplication, generally you can just do it directly. There's nothing to worry about. In your calculator, you might see the letter E instead of times 10 to the power of X, like what I have here in this calculator. But either way, that means the same thing. So sometimes you might just type in 7.50 E and then the power after that. In this case, I press that number and then I would put in the power that I want, which is 14. And then just make sure that this goes to then multiply, and the multiply is for the entire number, not just the power. Sometimes people make a mistake and they do multiply right here at the top. That would be wrong. You should multiply here at the bottom, which just means that it's multiplying that entire number. And then the other number is 6.22 times 10 to the 8. Okay, execute and you'll get your answer. So you can see the answer here is given in E. That's 4.665 E to the 23rd. It just means 4.665 times 10 to the power 23rd. Now, the one that's a little bit more difficult is division. And in this case, you're going to need to use some parentheses to do that. First number in parentheses, so 1.34 times 10 to the 8, and then close parentheses. So I would do it that way. And then you do your division here. So you do divide, and it might look like this. It might look like a division symbol. And then you put another parentheses and the other number. So 5.21 exponent times 10 to the -3, and then execute. And so this would be your answer. What people often make a mistake of is they don't use the parentheses, and in some calculators they're not able to actually figure out the order of operation correctly, so they might only divide with the 5.21 and then multiply later on by 10 to the -3 on the numerator. So it gives you the wrong answer as a result of it. This particular calculator is able to do it even without the parentheses, but again, not every calculator would do that, and I know that many of the scientific calculators that we often use for a class like this would require you to put these parentheses in. So just keep that in mind when you're working through this math. Now we can discuss the chemistry concept in this chapter, and that starts with the discussion of light, because we're going to get into solar radiation. Radiation is just a way to transfer energy from one object to another, and in this method of energy transfer, we're using light as the medium where that energy is being transferred. So if the sun is trying to transfer energy to Earth, it goes through these different light waves. Now, we need to understand that light is modeled as a wave, and it contains both electric and magnetic components, and that's the reason why we call it the electromagnetic or EM radiation. All waves, whether it's electromagnetic or any other waves that you might see, for example, in the ocean, they have three components that define them. So there is wavelength, which is just the distance between the peaks of these waves. So waves are illustrated by these squiggly lines. This is the wavelength of this particular wave. This is the wavelength of that particular wave, and this wavelength is shorter than that wavelength. And it's just given the symbol lambda, and it's given a unit of meter or some kind of a prefix that's attached to meter, depending on how long or how short that wavelength is. Frequency is another component of a wave. It has this symbol, looks like a V, but it's actually the Greek letter nu, N-U, and it just measures the number of waves that pass through a specific point. So for example, if I'm starting my stopwatch and then I stop it a second later and I measure how many complete waves have gone through. In this particular case, we got one wave here, another wave here, and another wave here. So there's 3 waves that pass through this 1 second time period. Then that means the frequency is 3 cycles per second, or we have another unit that we use the symbol Hz, which is called hertz. And then we have a third quantity that defines wave, which is the speed of the wave. Now, specifically when we're talking about electromagnetic electromagnetic radiation, that speed is given the symbol c, which is just how fast this EM wave is moving. The speed of light in a vacuum is always 3 times 10 to the 8 meters per second. These three quantities are related to each other. If you multiply lambda, which is the wavelength, times nu, frequency, gives you speed of light. Okay, so let's now work on one of the examples on how to use the formula that I've showed you in the previous discussion. So the example I'm going to go through is this one right here that says what's the frequency of a wave from orange light that has a wavelength of 602 nanometers. So we're given wavelength or lambda 602 nanometers and we're asked for frequency or nu. And the way you want to approach this is you want to go back to one of the equations, which is this equation right here for light, where c is equal to lambda times nu. C, remember, is the speed of light. So if we start with that equation and then we divide both sides by lambda to isolate the nu, we should get the equation at the bottom, which is nu is equal to c over lambda. Can cancel out one of the lambdas on one side. And once you have it in that format, then you can go ahead and plug in your numbers, 3 times 10 to the 8 meter per second for the speed of light. And the wavelength here is 602 nanometers, which you want to convert to meters to cancel out with the speed unit. And the conversion should look like that. And if you plug this into your calculator, you should get 4.98 times 10 to the 14 per second. And remember that that is a unit of frequency, or more commonly, we would just write it as hertz. I can talk about the wave itself, but when you see light, you don't see wave. What you see is just color. Those colors are actually what the frequency and wavelength of the light is. So each color represents a particular wavelength or a particular collection of wavelengths. And since wavelength and frequency are related by speed of light, once you know the wavelength, you can calculate the frequency as we just did in those examples. There's a lot of different types of light frequencies that are possible, but only a tiny portion is what we can see with our eyes. Those are what we call visible light. This picture right here shows you the whole entire range of light that is possible. And on the bottom right here is the wavelength values. So you can see that light waves go from as long as 10 to the 3rd meters all the way to as short as 10 to the minus 12 meters. So those are really, really short. So again, going back to that picture of waves, the really long one would have, you know, a really, really long distance it covers for one wave, where the short one would be really, really compressed like this one right here. The wavelength goes higher to the right, then the frequency is increasing the other direction, because frequency is inversely related to wavelength. Frequency is related to energy. So the higher the frequency, the higher the energy of that particular radiation. AM radio has a certain amount of radiation, but it's pretty much harmless to us. The frequency is pretty low. But as you go to X-rays, ultraviolet rays, those are dangerous to humans. It could mutate your DNA and so on. This whole range is called an electromagnetic spectrum, and there's just different types of radiation that's possible. And the ones that we can actually see is this really tiny region right here of visible light. As we just said, the frequency is related to energy. You can tell this when you actually look at the color of flames that's generated by different types of combustion. Some flames are hotter than others, and we can use a thermometer to measure how hot something is. Candlelight flame like this is not as hot as a stove flame, which is not as hot as these ones for welding. So there's different amount of energy associated with the color of the flame that you see. And of course, the frequency, which is the color that we see, determines the amount of energy of that particular light. So you can see it in that picture as well. Remember that frequency increases going to the left, so the energy also increases going to the left. Okay, you see it here at the top. Of course, wavelength is inversely proportional to frequency, so that if the frequency is higher, the wavelength is going to be lower, and so those both lead to a higher energy light. The lower frequency or a longer wavelength then lead to the lower energy light. This relationship you can write mathematically, called Planck's equation. He actually modeled light as a stream of particles that we call photons now, and the energy of one photon is E, which stands for energy, is equal to h times nu, frequency. So we call h Planck's constant. It has this value right here, and then the unit of energy in the end is joules. So when you multiply this times frequency, which is just 1/second, you end up canceling the seconds away and you get joules. Equation could also be written as hc over lambda if you want to express it with wavelength instead of frequency.
Let's take a look at two of these examples on the relationship between energy and frequency and wavelength for electromagnetic radiation. So the first one is asking you about these types of UV light, UVA, B, and C, and they have different wavelengths as illustrated there, 360, 300, and 240. The question is which of these is most harmful to humans? And the concept that you need to remember here is just the higher the frequency, the higher the energy. But remember that frequency and wavelength are inversely related. So if the frequency is high, then the wavelength is low. So the higher energy radiation is the one that's going to have the lowest wavelength. So in this case, when we look at UVA, B, and C, UVC has the lowest wavelength. So that's the one that's going to have the highest energy. And that's the one that's going to be most harmful to humans. Okay. The second question is asking you to actually calculate the energy of a photon of blue light. It has a wavelength of 401 nanometers. So we're going to just go ahead and use that Planck's equation. E is equal to h nu, but it's also can be written as hc over lambda. And I'm interested in using that second form because we're given wavelength in this case. Now, what you can do here is change this to meter because that will help us in the calculation. This becomes 401 times 10 to the minus 9 meter. Now, remember that you have to memorize some of these metric prefixes. Hopefully at this point you have memorized some of these. Now, the calculation itself is pretty straightforward. We're going to take that Planck's constant value of 6.26 times 10 to the minus 34 joules second, and then we'll multiply that by the speed of light in the vacuum as 3 times 10 to the 8 meter per second. So we're going to just use that number unless you're told some other number. Then you're going to divide now by the wavelength being 401 times 10 to the 9 meter. Okay, now this calculation might look a little difficult, but it actually allows you to cancel some stuff. So you notice that here I have denominator and numerator of seconds, and I can cancel that. Here I have a numerator and denominator of meters. I can cancel that. So notice that I just get a unit of joules at the end. That's the only thing that's left in terms of unit. And so the rest is just multiplying those numbers together and giving me 4.957 times 10 to the minus 19 joules. Now, you want to make sure that you have the right significant figures here. So again, those constants, you don't have to worry about them in terms of sig figs, but you want to look at the 401 nanometers that's given to you. So that's 3 significant figures number. So I'm going to give my final answer in this form. Okay.